Okay, so I wanted to make a the last part of part two of the video over practice quiz number 1 on non-equilibrium problems in accelerated motion. And we left off on problem 3 here, which is the last problem. Let me just erase a little bit of what's remaining here. Okay, it says a 20 kilogram block of compressed hash browns with ketchup has a coefficient of kinetic friction with an inclined plane of 0.4. What is the magnitude of the spud's acceleration down the ramp if it is inclined at 35 degrees? So let's go ahead and draw this ramp and this 35-degree angle. So maybe something about like right there and relative to this dotted line. And so this is going to be a tilted axis problem. And this will be our theta value. Go ahead and color that yellow or highlight it yellow. And but obviously what's going to be different from our normal tilted axis problem is that this object is not going to be in equilibrium in the x direction. It is going to be moving and speeding up. So we'll start here with the free body diagram of our block of compressed hash browns. And this is 20 kilograms as well. And what else can we say here? The coefficient, mu, so we can write mu k is equal to 0.4. So first thing we want to start with after we've drawn the situation is to go ahead and do a free body diagram. So let's go ahead and add that in. I'm going to zoom in here. Pick a different color here. Let's go with, I don't know. Let's go with brown. All right. So we have obviously force gravity pointing down. We have force normal pointing normal or 90 degrees to the surface. We have force friction. It's moving, it's accelerating down the inclined plane. And so the force friction kinetic will point up the ramp. Okay, so something like that. And those are our only three forces, right? There is no force down the ramp. Well, it is just gravity. A component of gravity will point down the ramp. So the idea here being that we need to tilt the axis system, or the coordinate axis, so it'll look like this. And let's call down the ramp positive x, because it's accelerating down the ramp, and maybe we just want the acceleration to be positive, right? And we can do that. So let's go ahead and give it a try, because I think that's something I've mentioned and we haven't normally done. All right, so there's our coordinate axis system right there, just slightly different than normal. So we have to get force gravity to agree with that. Let's go ahead and add some components here. So we'll call this FGY. I always draw that opposing force normal. That's how I know how to point it. And then obviously head to tail with that is this vector pointing down the incline, which is FGX. This sets up a 9-degree right triangle. And there's my right angle right there. It also puts the angle of theta, or 35 degrees right there. Okay. So we can see we have a SOHCAHTOA opportunity here. The hypotenuse will be FG, the adjacent FGY, and FGX will be the opposite. All right, so far so good. If we did a redraw step, just rather quickly, I'll just sketch it out. It would look like something like this right here. And what we're predicting is that this vector going down the incline will be larger than F friction kinetic. So yeah, just want to point that out because Fg of x will be larger than force friction kinetic because it's accelerated motion down the ramp, so therefore the force down the ramp is larger. Okay, so there's our redraw step if we choose to do it, not having to draw Fg in there. Okay, let's see here. So, where to start, right? I guess, well, we just pick a direction to work in. It seems like we care about the x direction, so let's go ahead and start there with solving. Maybe we can not have to worry about the y direction, but we'll see. So, sigma fx is equal to max. Our x forces, we call down the ramp positive x. So we got force gravity in the x direction is positive and force friction kinetic is negative. Set it equal to the mass, which I believe was 36, I can't remember, 20? 20, okay. And the acceleration, we don't know. All right, so far so good. FGX is an opposite, so we're gonna have to do a little SOHCAHTOA here. We can probably write that right here. So I think we have the sine of 35 is equal to FGX over FG. FG is always the same as mg. So we can go ahead then and multiply both sides by mg. Cancel those. Rewrite what we got here. FGX is equal to mg sine 35. M is obviously 20. Baby g is 9.81 meters per second squared. Sine 35 degrees. Let's get our calculator here and plug this in. Okay, let's see what this says here. Making sure we're in degrees. I'm getting about 112.54 newtons. All right. So, all right. So we have that, which we can then sub back into our equation. Now, we know that force friction kinetic has another formula, right? It's equal to mu times Fn. And this is going to be mu kinetic. So we're just going to make that substitution right there. So that's just a good formula to memorize, right? and because it's nice to sub into the problem when you need it, and that is that force friction kinetic equals mu kinetic times Fn. So that's the formula right there that I'm using to sub in and keep the problem moving forward. Okay, so coming back to here. So we have a problem here in that we're kind of stuck here because although we know mu kinetic, we said it was 0.4. Okay, let's go ahead and plug that in. We don't have something for force normal. So what we need to do is get force normal from the y direction. So I'm just going to hold it right there to get an expression for force normal. So then move to the y direction. If you want, I can finish writing what I have here. But you can see the reason I know that is because I have two unknowns, and therefore I need another equation. So I'm just kind of stuck with this right here. Just got to kind of pause it and get an expression for force normal or an answer for force normal and then plug it in. Okay, so let's move to the y direction. Now what's important to realize here is that the hash brown block, while it is accelerating down the ramp, is not accelerating in the new y direction. Therefore, force normal and FGY are going to be equal. And that's what we expect to see down here. So because there's no acceleration in the y direction, the hash browns aren't accelerating into the sky or into the plane, AY is 0, and therefore it doesn't matter what our mass is, the 20 kilograms times 0 is 0. So we have Fn pointed in the positive y minus FGY. And that's equal to 0. We can then see that Fn is equal to FGY. All right, so once we get FGY, we know Fn. So we'll go ahead and FG of y is if we look at this triangle, is an adjacent. So let's go ahead and use some cosine to solve this. All right. FG is really just mg. Multiply both sides by mg. Send it over there. The mass was, I believe it was 20. All right, go ahead and plug this in our calculator. All right, I'm getting about 160.72. Units are going to be newtons. All right, so we'll go ahead and sub that in. Over here, we can see that force normal then is equal to 160.72 newtons. Okay, so then that can then go back up here. Right. Okay. So I don't know if you can read that. Hopefully you can. There's a 1 out in front there. All right then. So we can go ahead and multiply that by 0.4. Gives us about 64.29. Okay. And if we subtract that, I think it's going to be, I guess, a little less. I thought it was close to half, but I guess it's not. No. It's less, a lot less than half. Yeah, it's double that would be 128. So I'm getting about 48.25. All right, so we can go ahead and divide here by 20 with the kg. And what we're going to see is these obviously cancel. AX then is equal to 48.25 newtons over 20 kg. And that is about 2.41 meters per second per second. All right, and that is our final answer. Direction is the positive x direction. You can also just add some text there and just describe it. So you can say down the incline or down the ramp. All right, so there it is. So pretty straightforward. I think we solved it pretty much the same as we would normally do for an inclined plane problem. And the only difference was that in the x direction, our acceleration was not 0. We left it as a sub x, and ended up solving for it as 2.41 meters per second squared down the ramp. And that's it. All right.